Good afternoon, everyone. This is Alan Pincus, the 3D printer business manager for Design Point Solutions, and I appreciate everyone tuning in today for today's webinar. If you're looking at your screen, it will show you a topic different than what you perhaps were expecting. Most of you, I believe, tuned in for Going Beyond Concepts, 3D printing of functional parts. That was supposed to be today's topic. Unfortunately, I've had some technical difficulties, just came up with the presentation, and rather than try to force my way through the presentation, we will just reschedule that for another day. And because of the number of requests I was getting, a lot of people wanted to talk about SLA technology again anyway. So I'm going to go through the gold standard of 3D printing, SLA technology. This was originally, did this on October 3rd, so on this eve before Thanksgiving, listen to me, I apologize. Halloween, on this eve of Halloween, I thought we would just run through it again, so I apologize for those out there who are expecting something different, but hopefully this will be useful for those who are not familiar with it anyway. So let's just jump right in. So today's agenda is fairly straightforward. We're going to do an overview of SLA technology, how it works, and how SLA is different from other technologies, and why customers, developers, people out there would choose SLA over other technologies, and do some comparison of SLA technology versus PolyJet, which is one of the competitive technologies to SLA. And then at the very end, a little Q&A. So if you're interested in asking some questions along the way, please feel free to type them in the webinar interface. And then at the end, I'll go through as many questions as I can as time allows. And I'll see the questions appear on my interface as well. So SLA, for those who don't know, stands for Stereolithography Apparatus. And it was invented in 1986 by Charles Hull, and he happens to be the founder of 3D Systems. So SLA has been around for 30 years, around 30 years now. And despite the emerging technologies over the past 3 decades, SLA remains the standard of excellence for creating strong, high-resolution parts with fine surface finish. And in the spirit of what I was going to talk about today, 3D functional parts, SLA would be one of the key technologies where you could absolutely make some functional parts and count on them to be strong, good representatives of the real thing that you ultimately produce. Again, this is a bit of a primer, so for those who are familiar with SLA, if you'll just indulge me while I explain it to the listening audience. SLA technology takes a UV curable epoxy resin that's filled in a chamber in the base of the machine. So I'm not sure if everyone can see my cursor or not, but in the bottom of this machine there's a liquid resin that fills the tank to the surface, or close to the surface of the tank. And the next step is that there's a build platform sitting inside the chamber, and it starts at the surface of the resin, right at the surface of the resin, where a laser beam with the aid of a scanning system is focused on the surface of the resin. So we have a laser here. It's not a high-power laser. It's actually a relatively low-power laser. The laser energy goes into the scanning system, which is interfaced with the computer that tells the scanning system by steering mirrors where to aim the laser beam and focus it. And it will focus it on the surface of the resin, and anywhere that the resin has been exposed to the laser, it instantly changes state from a liquid to a solid. And that's how we start building our parts layer by layer by layer. And like I said, when exposed to the laser energy, the liquid resin solidifies. And once that's done, the platform is lowered into the resin about 1/1000th of an inch, and the next layer is traced out with the laser, solidifying the resin and curing it on the layer below. And this is repeated thousands of times throughout the entire build, layer upon layer upon layers. Each layer is cured and bonds to the layer below. the platform drops, and this is repeated over and over again. So let's review several of the leading printing technologies that are currently available so we can draw some comparisons to SLA. So there's FDM technology, which is known as, which stands for fused deposition material, and people are becoming more and more familiar with FDM technology, especially as more of these desktop units become available. Basically, a strand of thermoplastic material such as ABS or PLA is melted and resolidified in a particular pattern. A second support material may or may not also be required. So some of these machines use two different types of plastics. One plastic is the build material. The second plastic is what's known as a support material to aid in the creation of the part. That support material is later removed. In multi-jet technology, layers of liquid UV curable acrylate resin droplets are jetted onto a surface along with a temporary support material. Each layer of resin is exposed to a UV lamp and hardened. So it's similar to FDM insofar as it uses a support material to temporarily have all of the build material located in the correct location. Then it cures, and as each layer is built, a little support is used along the way, and at the very end, all of the support material is discarded. The next technology that's out there is a powder technology, and here a layer of composite powder material is spread uniformly over an entire build chamber. Each successive layer is bound to the previous layer through a binding agent that basically has been draws the part being built. So you have this layer of powder and it comes out with a binder. The binder is only put down where you specifically want it, and then the second layer comes down and adheres to the layer below, and this process is repeated over and over again until you've fully built your part. The interesting part about powder technology is that there is no second support material required. It uses the build material that was unbound, or there was no binder on it to actually support the next layer until that is bound, and you basically blow off that extra powder and can recover it and reuse it. This fed into the powder technology has been around for a long time, at least 20-25 years, and it's being used in other technologies. The latest technology is known as SLS technology, is selective laser sintering, and this is using the same notion of a powdered medium, but in this case, instead of it being a gypsum powder or something like that, it's actually a plastic powder like ABS or nylon, and it's spread over the build chamber. And instead of using a binder to hold things together, it actually uses a laser beam, similar to SLA in the sense that it's using a laser beam, but in this case it's not curing it, it's actually fusing the particles together using the energy of the laser to bind everything together to make it in the final shape that you're looking for. The nice thing about SLS technology is the final result is a pure plastic part. There are no UV curing agents in it. There are no binders. You literally have what is as close to injection molding capability as you can get without actually doing injection molding. Along the line of powder technology, we have DMS technology, which is known as direct metal sintering, and this is basically the same as SLS, very similar to the powder technology, but instead of using a plastic or a gypsum-based medium, it uses various metals or ceramic powders instead of plastics. And I've done a webinar on metal printing previously, and I'd be happy to do that again if people request it, to see that presentation again. But we're using all sorts of different metals, which include the steels, stainless steels, ferrous and non-ferrous. We're using titanium, we're using cobalt chromium, and a number of ceramics. Basically, in the 3D systems world, any powdered metal or ceramic powder can be fused together or sintered together to make objects in those various materials. So why choose SLA? So every technology, including SLA, does have advantages and limitations. So here are some reasons why SLA might be the right choice for your applications. There are a wide variety of epoxy resins, and they all have varying properties. And 3D Systems offers nearly 24 different materials and continues to add materials as time goes on. And these materials emulate polypropylenes, ABS plastics, PLAs, flexible plastics. SLA has a very wide array of plastic materials that can be used to create your final result. One of the big key advantages of SLA technology, and it's very popular in medical devices where they want to be able to see through the part, and popular with companies that are designing sunglasses, and excuse me, not sunglasses, but glasses, where they'd like to simulate the lens quickly. It has the most visually clear resin that mimics polycarbonate, and from what I can tell out there, what I've seen and heard, there is nothing that comes that close to such a crystal clear material separate from SLA technology. The SLA is also incredibly accurate. We have accuracies down to thousandths in all three axes, and it can create the crispest edges and corners without compare. So even though what we call the PolyJet or multi-jet technologies, the specifications rival that of SLA, it can't compare when it comes to the edges and corners that are created in using SLA technology. One of the key advantages to SLA is that you get beautiful surface finishing, and like I said, it rivals injection molded quality. Unlike the powdered technologies, one of the artifacts of any powdered technology is you get a slightly gritty finish, similar to 200 grit sandpaper, if you will, that you can either leave or you can then go further sand and try to smooth. The key advantage to the SLA is it gives you truly fine surface finish and detail that no other technology even comes close. You don't need any separate support material or binders required like other technologies. When there are supports, it's made from the same exact material. Those supports, the computer creates these little standoffs for supports. Those are literally wiped off during the cleaning process. It has relatively fast build speeds, especially when building multiple parts at the same time. It also has a very simple post-processing that requires minimal skill. My assumption here is that people are familiar enough with 3D printing technology. They understand what I mean when I say post-processing. If not, just understand that whenever you build a 3D printed part, some level of processing after it comes out of the printer is required. That may be removing support materials, that may be cleaning, that may be polishing. There are a few things left. I think over the next decade or more, we're going to see that get simpler and simpler and simpler. But where we are right now, there's still some level of support. Excuse me, post-processing that goes on, and the good news about SLA is if you compare it against a number of other technologies, it is very straightforward and takes minutes to take care of instead of hours like some technologies. FDM, for example, has a relatively lengthy support cleaning process where you're either breaking parts off by hand or using mechanical tools, or dropping it into a sodium hydroxide bath to dissolve off this support material. That can take as little as a couple hours and potentially as long as 12 to 14 hours from what I understand. There's also no dangerous post-processing agents used to dissolve away the supports. Oh, like I just said, like FDM technology, you use sodium hydroxide. For the SLA technology, that's not required at all. It uses very green cleaning agents to clean the create a bath to clean the parts. You don't have to worry about caustic chemicals that could potentially burn the skin. And there's no special facilities requirements. It is truly office friendly. You can literally put this machine next to the desk you work at, like you might a 2D printer. It may make a little more noise than you'd like. From a humming standpoint, it does throw off a little heat like any appliance would. But beyond that, there's no special ventilation requirements, plumbing requirements, or things like that. It is really an office-friendly piece of equipment. So what comes up often in discussions I have with my customers is that they're talking about a multi-jet, or also known as a PolyJet technology, and why SLA. PolyJet, just so you know, is the trademark of one of 3D Systems competitors. Their multi-jet technology. 3D Systems also makes a multi-jet technology. It's our 3500 series machine that does compete literally head-to-head with the PolyJet. But that's for a time for another webinar I've done to talk about. We can talk about the multi-jet with 3D Systems versus the PolyJet. Many claim that the PolyJet technology rivals that of the 3D Systems SLA technology because their stated resolution specifications are similar. We say that our resolution's about 1/1000th of an inch in all 3 dimensions, and PolyJet says, well, yep, they are as well, about 1/1000th of an inch in all 3 dimensions. But a photo is worth 1,000 words, so I have some examples I can show you here. So here are 2 images of the same exact bottle that was printed using 3D technology. The bottle on the right, this is PolyJet technology. The bottle on the left, SLA. When you look at this particular bottle up close, it is very, very hard to tell that it isn't even glass until you touch it and the texture is of a plastic. It doesn't give you that glass feel. It gives you a plastic feel, and it's really mind-blowing how much it resembles glass coming off of the SLA machine. The PolyJet machine, hopefully you can tell right here, much cloudier, and this is what they refer to as their best clear plastic. So if clear is something you really want to use, clear is something you're doing for your product designs, you have things you want to be able to run fluids through, see the fluids, you're creating lenses, things like that, and you want to simulate a clear bottle, there is nothing that comes close to SLA, and hopefully that shows a pretty clear distinction. Accuracy is another area where SLA truly blows the doors off of multi-jet technologies. On the left, hopefully it's apparent, this is a part that's been printed in SLA, and on the right, printed in PolyJet. And even though it's saying the same thing, 10 point versus 10 point, hopefully it's quite apparent that the crispness of the 10 outshines that of the 10 here, and the clarity of the word point, the crispness of the word point is far better than here as well. And I do want to reinforce that this is literally the same exact model file being printed on 2 different technologies, the SLA technology on the left and the PolyJet on the right, using both the high resolution of both printers. And if resolution and clarity is something you're striving for, their hands down SLA is the way to go. We continue. Concerns about precision come up. This again is the same exact build file. Now granted, it's under a microscope. These things we're trying to see, you do need to see under a microscope, but this should be fairly apparent at just how clear and crisp the SLA on the left is. You can see the small hole. I think that's only a couple thousandths, maybe 5/1000ths in diameter. And on the right, not only is it cloudy around the perimeter or fuzzy, you can't even see the hole, and I assure you these are the same files. So this is just the limitation of a multi-jet technology versus the crispness of the SLA technology. Another example, I was talking about crispness, here it is again. On the right, PolyJet, also known as Objet. These are the same files, again printed, one on PolyJet, on our ProJet 6000, 7000 series machine. They're basically the same machine, but one's just a larger build area than the other. You can see the crispness we're talking about, and they put a detail here that this width is about 0.4 millimeters. So it's what, 12 thousandths or so, 10 thousandths or so. And over here you can see where, first of all, in the background, this surface has far more layer lines than what you can see at the back of the SLA technology. So there's again, crispness, accuracy, precision. These are all things that people promote when they talk about the SLA and kind of don't talk so much about the PolyJet. So if you're looking for the highest resolution, highest detail, which most people who are looking at 3D systems equipment, they're looking for the crispness, the accuracy, the precision that only SLA can give you. So there's a number of printers in the SLA family. It starts with our ProJet 6000. It has a build volume of, this is all in inches, 10 by 10 by 10. And the retail price starting in the range of $225,000 to $275,000. So compared to other technologies, it's definitely more expensive starting right out of the gate. Our PolyJet technology starts at about $70,000 to give you a price comparison, and the PolyJet technology starts at about $40,000 to $50,000 for their entry machine. So we're talking about a big jump when it comes to cost, but even an even bigger jump when it comes to quality. I'm not trying to suggest that our PolyJet technology isn't a good technology. It's an excellent technology for the correct applications. Much of what's going on in the 3D printer world is driven by the application. So if you have no need for this ultra precise, ultra crisp, perfectly crystal clear type products, a good starting point would be perhaps our PolyJet technology. You'll spend significantly less money and still get an incredibly good product. The next machine up in the family is our ProJet 7000. These two machines are actually identical as far as technology, laser technology, the filled chamber, everything. The key difference just being that the build volume is significantly larger. It's 15 by 15 by 10. And these machines start around 350, go between 350 and 400,000. Again, based on configuration, there are a couple different configurations depending on your needs. After that, we start moving into our production series. These are, and by the way, these 6,000 and 7,000 you can definitely use for production. Touching base again on what the topic was supposed to be today, you can definitely build functional parts in any of these printers. You can print production parts in these printers. It all comes down to the return on investment. If you're building expensive plastic parts, each with a good resale value, good margins, you potentially could do all your production on these machines and not have to ever do any tooling whatsoever to make your production parts. So much the case that they've created two versions of the machines that they call production machines instead of what they call these professional machines. The iPro 8000, basically these are all the same technology. It's got a vat of resin in the base, and it's got a high performance, highly accurate laser up here that shines down. This build volume is 26 by 30 by 22. The price tag for this machine, given what it can do and the size of it, starts around $600,000 to $700,000. And then the big granddaddy machine is our Pro X 950, which literally has almost a 5-foot by 30-inch by 22-inch build volume. They are using this to print demonstratable engine blocks. Car companies are building full wide dashboard assemblies in these much larger machines, all in one shot, printing all of them to see how they're going to come out when they actually create their injection molded forms. So again, these are more on the higher end for cost. They start at $225,000, $225,000 and run upwards of $1 million. But hopefully you've seen where the advantages are with this equipment when it comes to the quality, the flexibility, the accuracy and precision over other technologies. So at this point, this is a relatively short presentation, but I do want to open it up if there's any questions. I don't have any questions right now, but again, if you'd like to reach me, if you have any specific questions or business needs, feel free to reach out to me. Again, my name is Alan Pincus, working for Design Point Solutions. There's my email address, apincus@design-point.com. My telephone is 732-669-0055, and I'm at extension 224. And so I appreciate your time. I'll give you some upcoming events. We always have some SolidWorks webinars and hands-on test drives going. Design Point Solutions is one of the premier resellers of SolidWorks 3D software tools. We do have monthly seminars. Again, I'm going to run the seminar we were supposed to run today. I plan on running it next month, so stay tuned for that. We have topics generally about scanning technology, our plastics printers, mixed material printers, SLA we just reviewed, SLS we've touched on, and our PolyJet series of printers. So if you're interested in any of these things, don't hesitate to reach out to me. I do have a couple questions here. Let me take a peek, see if I can answer them for you. So the first question is, how quickly does the technology advance? In other words, if you buy tech today, will the models you buy become obsolete in 3 years? So that's a great question. The best way to answer that is let's take SLA as an example. SLA has been around for 30 years, and it's still the gold standard. So SLA technology will probably be here another 50 years. It depends. What I think will happen is for the price, you will get larger build volumes. You will get more material choices. The investment in the capital will come down as they continue to make improvements. But there's a technology that is not likely to be displaced anytime soon, and the resolutions we're at are down to getting downwards of a thousandth of an inch kind of thing. I'm sure that they'll continue to push that boundary. When it comes to our plastics printers, there's been a huge investment from 3D Systems and other companies such as Stratasys in promoting that line of UV curable plastics. So for that to be obsolete in 3 years is also highly unlikely. It will continue, my guess is, to evolve. It'll get faster. It will get less expensive. The build volumes will continue to grow. So I don't think we're looking at any obsolescence issues in that kind of time period. I think we'll just continue to see change in that time period where prices are coming down and capabilities are going up. The next question I have is material strength of printed material as a percentage of solid material. Okay, so we do get that question quite a lot. On 3D Systems website, 3dsystems.com, you can select any of their printer categories, their personal, production, and professional series. And in there, when you select one of the printers, you'll find the materials that you can choose. You'll want to bring up those material sheets, and in there are the technical specifications on the materials. So for example, they make a material that's ABS-like. They don't call it ABS because technically it's not ABS. It just has mechanical properties that come awfully close to ABS type properties. These are all acrylate-based resins that have UV binders in them, UV curable binders. So I'm not sure I did a good job answering that question, but starting with the strength of the materials and the data sheets would be a good place. And let's see here. I think that's the last question I've got. If you have any other questions, please, again, if I go back a slide, here's my contact information. Oh, definitely not going. Well, my contact information is Alan Pincus at apincus@design-point.com, 732-669-0055, extension 224. Please feel free to send me an email or reach out, give me a call, and I'll look forward to answering your questions and seeing you again at a future webinar. Thanks for your time, and talk to you soon.